So hi everyone, my name is Sherif, and I'm presenting today an approach to produce machine learning descriptors for materials. We call this approach the robust one-shot ab initio descriptors, or ROSA. So I'm going to be calling it ROSA throughout. This ROSA feature, or a set of descriptors, is able to describe materials for machine learning models and enable accurate training of machine learning models for various targets. So what I'm going to be doing today is I will go quickly through a few slides to explain what ROSA is about, what the problem is, first of all, and where ROSA fits in the spectrum of machine learning descriptors. And then we're going to switch to a fully hands-on session on how to use the ROSA Python code. It's all Python, by the way. Okay, the problem that we have here is we've got a lot of data on the internet, free online material databases such as Materials Project and AFlow and all those. And they have plenty of plenty of material structured data, such as the CIF file, the CIF file that describes the material crystallography as well as atomic positions, and corresponding DFT calculated properties such as the electronic band gap, the formation energy, mechanical properties, and all those. Now, if we want to predict properties such as those, one will need to do DFT, and people have been doing DFT plenty, like a lot of DFT, burning huge number of CPU hours over there, I think in the United States and possibly other countries, to produce these data sets. So it actually requires a lot of resources to be able to produce DFT calculations for materials. What if you want to predict those properties, such as the band gap, mechanical, elastic constants, and all these, the elastic constants, if you want to predict them without having to do the DFT calculation? So we have a lot of data available, but we still have, an infinite space for exploration. You invent a new material or you discover a new material. There is no facility to perform a DFT calculation to compute its band gap, for example. So how can we use this amount of data in order to help us predict the properties for new materials? Machine learning is obviously what people use in order to what has becoming almost a fashion in material science, trended very, very, very aggressively over the last few years, and now almost everybody is using machine learning by crunching all the data that's available on websites such as AFlow or Materials Project to train machine learning models to predict properties. So if you have a material that is not among these materials, you can pass it through your machine learning model that was trained on these materials and then produce the property that you're after. So that's in the outset, the problem of machine learning, the problem that machine learning solves in material science. Now, the key issue with, or the key challenging point in this problem is, how do we represent a material to a machine learning model? So I just said that materials are represented as CIF files, right? Which is the CIF file, very well known to material scientists, that represents the lattice structure of the material as well as the atomic positions within the lattice structure. Now, how do we represent this CIF file to a machine learning model? There are so many different ways people have approached this problem. So let me just, in the outset, let me just tell you what the workflow that we're trying to apply using machine learning is, and where this particular challenge fits in. So the workflow is, we have a material, we describe it, generate a data set, and then train the machine learning model. So the key problem that I'm discussing in this slide is the first part, describing a material to the machine learning model in order to build data set. So the data set could be an Excel file, like, just a table. Each row is a material identifier and each column is a value or a descriptor. How do we get to these values or these descriptors? So many different solutions have been proposed in the literature, such as generalized neural network representation using symmetry functions, the PLMFs, and the CGCNNs, which use graph networks coupled with convolutional neural networks to describe materials, scalable way to describe materials. And by the way, this has been really hot in the literature for many reasons. It has been applied for a lot of different, for predicting a lot of different properties for a wide range of materials, and very successfully, delivering high accuracy. Now, the thing with this approach and several other approaches is that they are very geometry dependent. So they depend so much on the geometry of the material. And when you depend so much on the geometry of the material, this means that you have to come up with descriptors derived from the geometrical structure and the lattice structure. We know that we cannot, for a material which has, 3D periodicity, we cannot describe the material structure via its atomic position. I mean, for example, you want to describe diamond, you cannot just use the positions of the 4 carbon atoms in the unit cell of diamond. So that's the unit cell here, which forms a crystal in, infinite in all the dimensions. So if you want to describe diamond and you think that you can rely on the XYZ positions of the 4 atoms, what happens if you take another snapshot or another bit from this crystal structure and try to describe it using the atomic positions, such as that bit? So this can also be, this is also a valid unit cell for diamond, but it has different XYZ positions. We cannot use the XYZ positions in order to, like the absolute values for the XYZs in order to describe diamond. Let's think of, okay, how about using the relative, distances, like the distances between the atoms? But the thing is, diamond has 4 atoms, like other systems have 8 atoms in the unit cell. And the unit cells can have different geometries and different structures. There's orthorhombic, there's hexagonal. So what we need to do is we need to find a way to describe the geometry in an invariant, in a translationary invariant way. And this has been done already in particularly in this and these two papers. So no matter how the geometry changes, the code or the algorithm that these authors wrote will translate your geometry into a set of numbers, right, that have nothing to do with the translation, how much you translate the unit cell. Remember that because of predefined conditions, you can translate the atomic positions and the unit cell stays the same, right? So this also has to apply to your descriptors. So these are geometry descriptors, right? There are other types of descriptors. There are descriptors that are depending only on the properties of the atoms inside the cell. But there is an issue with using such a descriptor. Let's say that you have diamond, for example, which is a phase of carbon, and you describe diamond in terms of the properties just of carbon atoms. What happens with graphene? Graphene is, or graphite, it's another phase of carbon, but it's completely different structurally, yet it has the same atomic composition, which is carbon. So if you're only relying on properties of just the elemental properties of the elements within the structure, you're going to be missing out on all the different phases. So for example, people who use just the stoichiometry or the formula in order to, as a descriptor are missing out on the possible phases that, for each of the materials. So that's another class of category of descriptors. So geometry descriptors, and there's also atom-based descriptors. Now the geometry descriptors have got this issue with interpretability. You build, in order to get a reasonably representative set of geometry descriptors, you might need to have a very large number of values or columns. For example, in this particular example, the authors had to represent the materials using a convolutional neural network, and the number of inputs for such a deep learning model is large, and the depth of that model represents an issue for interpreting the results of the model. How to make sense or how to connect between the input and the output. That's the interpretation, to make some physical sense or chemical sense between the input and the output. If the input is transparent to physical interpretation, then it will be easy, such as atomic-based descriptors. I mean, like for example, if one of the inputs is the mean of the atomic mass, and if this value can correlate with the target property, then we are able to interpret the target property in terms of its input. However, in geometry-based descriptors, particularly this and this example, the GNN's generalized neural network representation by the Perennial group and Jeffrey Grossman's and Tianchi and Jeffrey Grossman's very famous, now famous, the CGNNs. The input is quite complicated. There is another category of descriptors, and which is based on ab initio calculations. So you want to predict the value, for example, of a material, a value of, let's say, the band gap at a certain level of theory, let's say at a B3-lip level of theory. And to be able to obtain that value, you need to perform a DFT calculation using Gaussian, for example, that requires 8 or 16 cores. You cannot do such a calculation on your PC, otherwise you'll have to wait for quite a long time. However, there has been a trend recently where people have been using or performing DFT calculations at a very low level of theory in order to generate descriptors, such as the frontier orbital's energies. So you got a molecule, you want to predict the, let's say, polarizability, or you want to predict the high level, the homo-lumo gap of the molecule at a very high level of theory, GW level of theory, for example. So what you do is you perform a DFT calculation using B3-lip or a PBE on the molecule in order to obtain the eigenvalues, and take those eigenvalues as inputs to a machine learning model in order to predict the homo-lumo gap at a higher level of theory. So these are ab initio descriptors. They are costly to perform. You have to do the entire, you have to solve the DFT problem, or the DFT equation, in order to generate those ab initio descriptors. So now, the good thing about ab initio descriptors is that they are very interpretable. I mean, it's very obvious what they mean. So homo-lumo, for example, or the homo -1, homo -2, and then homo, lumo, lumo +1, lumo +2. If you use these as descriptors into, let's say, a simple model such as a very shallow neural network or an XGBoost model, for example, you don't have to spend so much effort in order to interpret the results, because the descriptors are meaningful, which is different from the situation when you have a vast amount of values to describe the geometry in a translationally invariant way, but it's hard to pinpoint what each value means. So between geometry and its opaqueness to interpretation, ab initio descriptors and their their transparency for interpretation, I found that we can fill a gap here and come up with ab initio descriptors that are very, very shallow, performed at not even at a full level of theory, like at the DFT PBE, for example. You don't even need to do the DFT PBE in full, not the SCF cycle in full, just one iteration, not a full iteration. So when you do the SCF to calculate, the total energy of the system, you have to wait until all, the energy total energy of the system converges. Without waiting, you just take, so what the idea here behind ROSA is, you don't wait, you just do one step of the SCF cycle, and that's it. You just take the eigenvalues coming out from that one step. This is definitely much quicker than a full ab initio calculation for your ab initio descriptors, and it is still giving you the transparency you need in order to interpret your machine learning model, the outcome of the machine learning model. So that's the idea of ROSA in a nutshell. And here, that's this slide has got this figure that basically explains ROSA, schematically. So if you do a DFT calculation, so the energies before the optimization are some numbers that are very inaccurate, not directly related to the energies after the optimization. When I say energies, I mean eigenvalues, total energies, total exchange energy, all these values. In ROSA, you just do the first step of the the energy calculations, and you stop there, and you give those energies to your machine learning model, symbolized here with this brain, train it in order to predict the higher level of theory energy values, such as the homolumo gap or the band gap for a crystal structure. So there is a lot of time saving here, and there's also, we're still maintaining the ability to interpret the outcome of the model. To be able to produce those descriptors, we can use a DFT code that runs on the computer, just on a PC. DFT doesn't only run on supercomputers, and it's not only in Fortran. There is actually a DFT code that has a really nice Python interface, which is GPO, and you can install GPO on your computer and run it and perform full DFT calculations with GPO. For the sake of ROSA, we are going to be using GPO at a very the minimal level of theory, and also we'll have to modify GPO so that it can be comfortable performing only one iteration of the SCF cycle. This requires a very slight modification of GPO, which I'm going to be putting, which is actually available on the GitHub for ROSA. Okay, so the output of this procedure is the eigenvalues, the total energy component, or the components of total energy. We take those as descriptors, as simple as that. And the results actually were quite interesting, were quite remarkable. So an R square, so we generated the ROSA descriptors for how many, like 39,000 materials from materials project, in order to predict the band gap, and the R squared that we got was 0.87, very, very close to the value of 0.9, which has been cited in the literature by other approaches. And I think with a larger data set, we can actually drop that number a little bit more. The mean absolute error is 0.23, which is very, very competitive, a competitive level, accuracy compared to other, descriptors. The formation energy was remarkably accurate, 0.97. And by the way, remember that when we built these models, we described each material in terms of ROSA as well as other sets of descriptors, which I'm going to be talking about in the following hands-on part of the tutorial. And sometimes you would have ROSA more predictive of a certain quantity than other descriptors, but the other descriptors more predictive for certain other quantities than ROSA. That happens, that's completely fine. But it's good to have all those features in your machine learning, in your data set, to encompass as much diversity of properties as possible. Okay, so like this, for example, this figure, for example, that's for the band gap prediction, and this correlation plot is for the formation energy prediction, which is 0.97 R squared, which is quite high. Okay, that's all for the tutorial. So sorry, for the presentation. Now I would like to show you an example of how to actually use ROSA. So in order to do that, I have uploaded or created a repository just for to practice using ROSA. So this tutorial has got code Python code as well as the outputs for using ROSA, as well as some other features in order to learn and predict the band gap of a small number of perovskites. So this data set here is quite a small data set, like 700. We don't expect a lot of accuracy here, but it's just to master the art of using the ROSA code as well as using that other feature code in order to build a data set, train a very basic machine learning model, and visualize the results. So the first step of this code of using this repository, so that's the repository here, and I'm going to put that in the that web address into the chat if anyone is interested to copy paste it. Okay, so the first step here is to go to generate data, and let's just go through this code. So generate data.py is a Python code that first of all accesses materials project, retrieves all materials that have the ABC3 formula in such that one of the A and B and C is an oxygen. And when you do this, actually the largest majority of the materials we're going to retrieve are going to be perovskites, AbO3. Very, very few, maybe handful, are going to have oxygen in place of A or B. Let's just not worry about those. For the sake of practice, I'm just going to be using this simple query in order to get that number of perovskites from materials project. And also I'm limiting the number of sites to 20, and the band gap has to be above 1, basically to reduce the number or the size of the data set for the sake of the exercise. So the second thing is we're going to be, after retrieving the results of this query into the results variable, we open a new file, tutorial.json, and store results into that. And and then we produce a data set. So we iterate through results and then grab the CIF string from each entry in the results array, which we obtained from materials project, and use descriptors rosa.descriptors, the descriptors function in the descriptors underscore rosa module, which is also available in the repository, and pass the CIF string to it. And sometimes, for some reasons, you have a CIF file that might be problematic or might not be. Like, for example, you might get a CIF file from some source, but it has been structured in a way that that cannot be read by the ASE Python library. So, GPO relies on the ASE Python library for opening and reading and writing files, structures files. So if ASE cannot interpret it, there's going to be a problem, an error. And so what I do here is, if there's nothing returned from the ROSA calculation, this means that the array is going to be empty, in which case we're going to report the problem in the material. Otherwise, we're going to be adding the result to the dataset array, and also we're going to be grabbing the band gap value from, as you can see here, we're in the properties section of the query, or the properties parameter in the query. We're grabbing the material ID, pretty formula for the material, the CIF string, band gap, energy per atom, formation energy per atom, the energy above hull, and created at. I added a few more here for your information. You might like to use them. You might want to actually apply this tutorial to train a machine learning model based on formation energy per atom after we're done with the band gap. So we're going to be focusing here just on the band gap training the machine learning model to predict the band gap. So after that, after this loop finishes, we save the dataset in dataset underscore rosa. And that's going to be like a CSV file that has got all the ROSA descriptors for all the materials in this data set. Now let's see this in action. So I'm going to go here. Just remove those. Just kill this. Okay. Here's the code. I think I just discovered that there is an error here. Apologies. Dataset D. I'm gonna correct, sorry, the repository code. So we get D, and then we add it to the dataset. And after that, we create data frame based on it, save the data frame in, and add the band gap column, material ID column to the data frame, and then save the data frame into a CSV file. And then after that, we generate another dataset with a different feature in a separate CSV file. That other dataset is based on the VACD, or the basic atomic atom-based and crystal descriptors, which I have already covered in a previous tutorial on the Exciton Science YouTube channel. And the code, so the code for BACD descriptors, the basic ones, as well as for the ROSA descriptors, is available here, which is also available on the GitHub repository. And I'm going to be describing those two very, very briefly now. So once we generate the VACD descriptors, we save the dataset again in a separate CSV file. And then later, we're going to merge the two descriptor sets, or the two CSVs, or the two, sorry, data frames from the CSVs into one large data set. It's always a good practice not to mix all of your descriptors into one CSV file. Separate, put them into separate CSV files. Maybe later you want to merge them together, or you want to merge a few of them together, or merge them all together, but it gives you the freedom, to merge any number of them together. Okay, so after we generate datasets, let me just very, very quickly show you how this is going to work. So I'm going to put Python. And the first part, let me run this part first. So this part retrieves the data from materials project, and let's see how many materials are returned. 780. So only 780 is a very small data set. You don't expect a lot of accuracy training any machine learning model based on a data set like that. Sometimes it happens for certain quantities or certain target properties to be predictable with a small data set. And I've seen many examples in my own work and other people's work about this. But for the band gap, you do need wider variety of materials to be able to make accurate predictions. Accurate, I mean near 0.9 R square, that sort of accurate. Okay, so now we retrieve data set. And we've saved it into tutorial.json here. And the next step is we create those arrays, empty arrays, and then generate the ROSA descriptors. So let me run this and show you how it works. Now, ROSA descriptors, they are DFT calculations, just a singles or a one shot, but it is still a DFT calculation. So it takes a bit of time. Let's see how much time it takes on this 6-core. Yeah, so that's nearly the amount of time it takes on an Intel i7 core Alienware laptop. It is, as you can see, it's not really as quick as other descriptors, such as the atom-based descriptors. So let me show you, for example, I'll just stop this because I've got that data set already stored here. I'm going to show you, we're going to be using that one in our machine learning exercise. Now, let's see what happens when we create the VACD descriptors. Of course, it's going to be super quick because the VACD descriptors are based on just properties of the atoms, just some statistics based on the properties of the atoms. So let's just go quickly through the VACD code. So in the VACD code, we are collecting the distance metrics, performing statistics on it, atomic numbers, van der Waals radii, electrical resistivity. All of these are quantities that we obtain from the periodic table of each of the elements, for each of the elements. So there is nothing, we don't do heavy calculations here, right? So it's very quick. As you can see, 780 finished in a few seconds. Whereas in ROSA, what we do is we have to calculate, first generate a GPO object to perform a DFT calculation, and then perform a calculation. So calculate performs a DFT, but that DFT, as I said earlier, is only one step in the iteration. That's why we have max iter equals 1. Okay. So the code is out there if you'd like to have a look. We don't have enough time today to, or in this tutorial, to go through every bit of the code. The purpose here is just to present the code briefly and then go in some detail in the machine learning workflow, generating the script, downloading materials, generating descriptors, and then performing machine learning. So this takes us now to ml.py, which is the machine learning code. And in the machine learning code, we're going to be doing the following. We're going to be, first of all, we're creating an XGBoost regression object. Small number of estimators, just 100. Maximum depth, 100. You can change these parameters if you want. Random state equals 0. And then we're going to be reading the ROSA and the BACD datasets into separate data frames, and then merge them into the full dataset underscore df. And having merged them, having done the merger, one might need to clean up the data. Sometimes, when some of the DFT calculations in ROSA are performed for certain material structures, some quantities get at the has the inf or the INF value. And this is something that I'm still working on to fix. But for the sake of exercise, we can just remove any records that have got inf values or NaN, not a number, values. So that's the purpose of these two lines. And then when we merge them, when we merge those two data sets, we get the unnamed column, or the column that was reserved for, like artificial index 0, 1, 2, 3, 4. We just need to remove it. And that's what we do here. And then we report dataset size. So let me just run these lines here. First, dataset size is 780 materials, 544. So that we've got 544 columns. Okay. 327, I think, out of those are for the BACD descriptors, and the rest 218 are for the ROSA descriptors. Next up is creating the training data and the test data. So Y here, that's the output or the target, equals full dataset energy. And let me just show you the columns in full dataset. So columns. So these are all, unnamed columns, but the last one, that's the band gaps. So we need to get the band gaps column, put it in Y, energy, the value of the energy, that's a variable. This value is band gaps. X equals full dataset, and then we remove that column from X. We cannot have the target in the X, of course. So we have the X and the Y. We use the train test split scikit-learn function in order to split the train and test. And let's just do it here, 80-20. Of course, one might need to do a 5-fold training where you perform this exercise 5 times with different shuffling of the training and testing, but haven't done that here. That's just for the sake of a quick, tutorial. You can do this on your own later. And then we normalize the training and the test inputs based on the training set. And we save that scaling or normalization, into the saved models folder. You do need, when you create a machine learning model to predict or to use it to extrapolate properties of materials that you don't have at the moment, then you have to keep all the models, both the machine learning model as well as the scaling model or the scalar model, in a safe place, in a folder. Okay, and then this is to save the datasets, the test and the train datasets. And now here we start the machine learning. Okay, so fit, this is where we use the fit function from XGBoost in order to fit our data. And interestingly, I actually need to just add 2 lines here. Apologies. Remove them by mistake. That import was deleted by mistake. Apologies for that. Okay, so let's actually run up to here. Isn't that the absolute error? Ah, there you go. So the mean absolute error. So we're calculating the MAE, the mean absolute error, as well as the R square. So I'll do is I'll just run everything up to that point, up to the training, and outputting the accuracy of our training. So after the fitting, we perform the prediction. So let me show you. So that code is, so regression to predict the outcome from the test inputs, and then compare that outcome against the input, or sorry, against the true value of of the band gaps, and calculate the mean absolute error and the R square. And the values we got 0.379, almost 0.38, and 0.75 for the R square. Reasonable. I mean, not too bad, given that we have a small data set. And of course, one would need to do to perform the fivefold, because and then take the average of these quantities from the fivefold cross validation, and in this case you might get better numbers. And after this code here, plots the correlation plots, right? So that one plots it for the test data. Let's have a look, because I've ran this before. So for the correlation of the test data set, it looks like this. So we've got, this is the DFT values versus the XGBoost values. And you can see that there is a reasonable alignment. However, when you do the training, we've got this overfitting issue where we have, which is very common in XGBoost. XGBoost very, very easily overfits, unless you're very careful with the structure of the XGBoost model. I haven't done that much here. Maybe in a previous tutorial, I'm just stuck to the simplest options in the XGBoost model. But it's, you can make your XGBoost tree much shallower. Reduce the number of estimators and all that in order to avoid, and of course tune other parameters to avoid overfitting. Okay, so that's the result for the test set, the correlation, and the training set, which definitely displays the overfitting I just discussed. And that's the code for performing the prediction based on the training set. And that's the code for performing the plotting based on the training set. So that's basically it. So what I've done is I performed, first of all, I ran the generate_data, which retrieves data from materials project, and then processes this data in order to produce our data set for two features. One feature is the ROSA features, and the other feature is the BACD, or the basic atom-based and crystal descriptors. After generate data, we used ml.py, which uses the generated dataset CSV files, merges them together, places the band gap target values into the y-axis, into a y vector, and places the input descriptors, the BACD as well as the ROSA, into the X, and performs the split, 80-20 split, scaling, and saving all these data into a folder, which is dataset folder, machine learning training, accuracy of the machine learning training for the test set, and then plotting the correlation plot, and then accuracy of the machine learning for the training set, which is obviously going to be higher, and then plotting the correlation plot for the training set. And that was it for today's tutorial.